Today we're going to talk about one topic we didn't quite get to completely last class, up and down sampling. It's actually changing the sampling frequency of your signal. It's an advanced topic. And a topic we bring up early in this class called symmetry. So we bring it up in the time domain because it's a time domain property, and you can see it in the time domain, but we really don't, it won't become clear why we care about it until we get into the frequency domain. There's a lot of subparts to symmetry. We'll talk about periodic versus aperiodic waveforms. And energy versus power waveforms. So these are all characteristics of sequences in the time domain. And the last we'll talk about if a sequence is absolutely summable or a square summable. Now, I've always been straight up with you guys. When there's a good lesson, I'll tell you it's a good lesson. This is going to be a harder, more boring lesson. There's going to be a lot of, we're talking about essentially a lot of vocabulary definitions. The vocabulary definitions will come into play later on when you get into the frequency domain, and this will all make sense why you're learning it. First is on upsampling. Now, the thing to keep in mind is it does not change your sequence at n equals 0. It does change the sampling frequency. So you've got this x of n, and it's going into an operator. That's an upsample operator. Let's say we upsample by L. There's no particular significance to the letter L other than that it's an integer. And I think it's easiest to give an example of what this does. So all of these operators we are going to use with a finite length signal. So here's a finite length signal of what length, Gordon? What's our capital N here for length?
4, sir.
Right. And that's a common misunderstanding, that even though the largest non-zero N is 3, it's a length 4 signal. And if we upsample it by, say, 3, what you will get out will be always the same signal at x naught, but then we'll insert an extra 2 zeros. In between them. So what was your signal at 1 is now at 3. What was at 2 is now 4. It is now rather 6. We just multiplied everything through. Now here's an interesting one. We've done the same thing for the signal at 3 too, even though it is 0. So we end up with this being 0, and then we insert another 2 zeros. So this whole sequence, and now notice there's nothing at 12, there's nothing at -1. It's a finite length signal in, finite length signal out. It was length 4, and our modified signal is length 12. You might have already heard of this used in practical applications. Have you ever heard of a CD player, or, oh my gosh, I'm dating myself, or an MP3 player, or perhaps an expensive type of A to D or D to A converter for your music that says it upsamples to 16 bits, or it's a ×4 oversampler times 4 sampler.
Yeah, I've seen that terminology get thrown around.
Yeah, thanks for the thanks for the assist, Eric. So again, this is what they're doing is they're throwing in extra 0 samples, which seems to include no extra information. But again, when we get into the frequency domain, it'll become clear what's going on. The way to say this mathematically is to say it's equal to our new signal is equal to our old signal divided by the upsampling amount if n over L is an integer, and otherwise it's 0. Its twin is downsampling. Downwards arrow. I'm using a different letter just to make it clear, but it's a different operation. But there's nothing special about M other than it is an integer. And let's say we've got a signal that looks like this. 0, 1, 2. We put that into a downsampler by 2. And again, it doesn't change your X if not, but it just throws away. It just throws away our intermediate point. So I actually gave it one too many here. Throws away that sample, throws away that sample. So it converted this 1, 2, 3, 4, 5-length signal to a 3-length signal. And here's my question. We're not going to talk much about upsampling and downsampling. I want you to have seen it someplace because it will become clear it's a graduate level topic, but it's how to take a signal that has limited information and upsample it, do some filtering on it that is more exact in the frequency domain on the upsampled signal, and then downsample it when you're done. It's a graduate level topic. But I want you just to think about how do you upsample by, say, 1.5? Anyone?
So what was the question?
How do you upsample a signal by 1.5? I showed you graphically how to do it by 3, also mathematically how to upsample. I didn't give you the mathematical definition for downsampling. It's in your text, but I showed you graphically the intuitive way. Tell me, how would you upsample by 1.5, or can you?
I think if we're operating in discrete time, then it shouldn't be possible.
Yeah, that's one way of saying it, that it shouldn't be possible.
Well, I mean, thinking about it from a MATLAB perspective, wasn't this on one of the labs where you had us do a lengthen thing and it added in extra signals that were averages in between integer values?
So one way is you could sort of approximate it by averaging between values. Yes, it's not clear how you'd average if you wanted to upsample it by, I don't know, 1.7, say. But yeah, there should be some way to get, if you start off with a signal of length 1 million, there should be a way of ending up with a signal that's 1.7 million with some sort of averaging thing going on. Here's a simple way to do it, just using upsampling and downsampling. You upsample by 3, followed by downsampling by 2. No averaging involved there. what we'd actually do is in between that stage, you'd filter the results and then you downsample by 2. And that would give you some sense of averaged signal. And how do you create the filter? It's a frequency domain thing. We'll talk about that in 2 exam blocks.